Before there were names like Milky Way, Virgo, Laniakea, or observable universe, there was a simpler mistake almost every human mind makes. We imagine space as a dark room filled with islands of light. A galaxy here, a galaxy there. A cluster in one direction, another cluster far beyond it. As if the universe were a giant black ocean and galaxies were scattered through it like sparks thrown into the night. But when astronomers began mapping the sky deeply enough, the picture changed. The galaxies were not arranged like random dust. They were not evenly spread. They were not floating alone in a quiet emptiness. On the largest scales we can measure, they formed strands, walls, knots, bridges, rivers, and enormous empty regions between them. The universe did not look like a room full of stars. It looked like a living network made from gravity, dark matter, gas, and time. And the strangest part is that this web is so large that entire galaxies become almost invisible inside it. The Milky Way is not the structure. It is only one small point caught inside the structure. Before we begin tonight's journey, if you enjoy calm space documentaries like this, please subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is right now where you live. It is always strange to remember that people can be watching the same universe from different places on Earth, under different skies, at different hours of the night. Tonight, you are watching the Just About Space channel, talking about the cosmic web is bigger than we can imagine. And to understand why, we have to begin not at the edge of the observable universe, but here, from the small place where the illusion starts. From the surface of Earth, the universe looks mostly empty. The sky gives us points of light. The eye sees stars, not structure. A telescope gives more points than patches of gas, than the faint smudges of distant galaxies. But all of these appear projected onto the sky, as if everything were pasted onto the inside of a black sphere around us. The nearest stars and the farthest galaxies seem to share the same ceiling. Depth is the first thing hidden from us. A bright star may be only a few dozen light years away. A faint galaxy may be hundreds of millions of light years behind it. Another dot may be a quasar, whose light has traveled for most of cosmic history. Without measuring distance, the sky is a painting, not a map. It shows direction, but it does not immediately show the true arrangement of things. This is why the cosmic web was not obvious for most of human history. You cannot see it by simply looking up. You need thousands, then millions, then billions of distance measurements. You need to know not only where an object appears in the sky, but how far away it is, how fast it is moving away, and how its light has been stretched by the expansion of space. Only then does the flat sky begin to open into a three-dimensional universe. When that happens, something unexpected appears. Galaxies gather along long chains. Those chains meet in dense intersections where galaxy clusters form. Around them stretch broad sheets of matter, like thin walls made from light. Between the walls are voids so wide that millions of light years can pass with almost nothing bright inside them. It is not a perfect spiderweb. It is not a machine with straight lines and clean geometry. It is messy, broken, curved, uneven, and alive with motion. But it is real enough that when astronomers map galaxy positions, the pattern keeps returning. The universe has a skeleton, not a skeleton made of bone, and not even mostly made of stars. It is a skeleton made largely of dark matter, shaped by gravity, filled with gas, decorated by galaxies, and stretched across distances that ordinary language was never built to hold. The first disturbing idea is that our galaxy is not traveling through empty space, as much as it is embedded in a vast cosmic landscape. The Milky Way sits inside the local group, a small collection of galaxies dominated by the Milky Way and Andromeda. Around us are dwarf galaxies, streams of stars, dark matter halos, and long histories of mergers. That already sounds large. Andromeda alone is about 2.5 million light-years away, far beyond any distance humans can practically imagine crossing. But the local group is still only a small neighborhood. Zoom out farther, and the local group becomes part of a broader flow of galaxies. Nearby galaxy groups and clusters are not simply sitting still. They move under mutual gravity. They fall toward denser regions. They drift with the expansion of the universe. They carry the marks of deeper structures around them. The Virgo cluster, containing thousands of galaxies, lies tens of millions of light-years away and acts as one important mass concentration in our cosmic surroundings. Beyond it are larger patterns, including superclusters and long filaments that connect regions of high density across enormous distances. This is where the mind begins to lose its grip. A galaxy cluster can contain hundreds or thousands of galaxies. A supercluster can contain many clusters and groups. A filament can stretch for hundreds of millions of light-years. A wall can appear as a sheet of galaxy-rich structure across a significant portion of the map. And between them, voids can be so wide that if the Milky Way lived inside one of their emptier regions, our view of the nearby universe would be much lonelier. A cosmic web is not an object you can fly around in a human lifetime. It is a pattern so large that light itself needs tens, hundreds, or even billions of years to reveal its shape. To picture it properly, imagine leaving Earth at impossible speed. First, the planet shrinks beneath you. The moon becomes a pale companion. The sun becomes one star among many. The solar system fades into a tiny arrangement inside the Orion arm of the Milky Way. Then, even the spiral arms blur. Dust lanes, star clouds, and clusters merge into one flat glowing disk. Keep moving. The Milky Way becomes a single bright island. Andromeda appears nearby on this scale, larger but still separated by a gulf that no spacecraft could cross quickly. The smaller galaxies around them become sparks. The local group takes shape. Then the local group itself shrinks. It becomes one bead inside a larger arrangement. Other groups appear. The Virgo cluster enters the scene, not as a cluster of individual galaxies anymore, but as a bright concentration in a wider flow. Faint bridges connect regions. Empty spaces open between them. Farther out, the picture stops being about galaxies and starts being about geography. There are highlands of matter and lowlands of darkness. There are rivers of galaxies and basins where few galaxies formed. There are knots where gravity gathered material for billions of years. And there are vast bubbles where matter drained away into the surrounding walls. At this scale, the universe no longer resembles a collection of separate objects. It resembles weather frozen into structure. Gravity has drawn matter into streams. Expansion has stretched the background. Dark matter has provided the invisible scaffolding. Ordinary matter has cooled, collapsed, ignited, and become the stars that let us trace the web at all. But the visible galaxies are not the web itself. They are more like lamps placed along a road. This matters because when we talk about the cosmic web, we are not only talking about what telescopes photograph directly. We are talking about a distribution of matter that includes dark matter, hot gas, faint gas, stars, galaxies, clusters, and the empty-looking regions between them. Much of the web is hard to see. Some of it is traced by galaxy positions. Some is inferred by gravity. Some is revealed by the bending of light. Some is suspected because normal matter seems to be hiding in thin, warm gas between galaxies. The web is larger than the glowing pieces that show it. That is one reason it feels so unreal. Human vision loves bright objects. Stars make sense. Planets make sense. Galaxies, though huge, still feel like things. They have edges, colors, centers, arms, shapes. You can put one on a screen and point to it. The cosmic web is different. You cannot point to it in one photograph and say, "There it is, complete." You can only build it from surveys, maps, simulations, redshifts, lensing patterns, temperature measurements, and theory. It exists at a scale where no single image can show the whole thing. It must be assembled in the mind. And once you assemble it, the universe becomes stranger, not simpler. The story begins with maps. The earliest maps of galaxies were not deep enough to show the full pattern. They revealed that galaxies were not evenly sprinkled, but the true web remained hidden. As surveys improved, astronomers measured more redshifts. Redshift is one of the key tools in cosmic cartography because expanding space stretches the light from distant galaxies. The more the light is stretched, generally, the farther and earlier the galaxy is being seen. With enough galaxies, each redshift becomes a depth marker. The flat sky begins to acquire distance. In redshift surveys, galaxies can be placed into three-dimensional volumes. Slice by slice, the universe begins to look foamy. It does not become smooth. It becomes more structured. The galaxies trace arcs, filaments, and broad walls. The voids between them become impossible to ignore. One of the most important lessons from these maps is that emptiness is not a background detail. Emptiness helps define the whole architecture. A void is not simply a place where astronomers forgot to look. It is a real low-density region, often spanning tens or hundreds of millions of light-years. Compared with filaments and clusters, voids contain far fewer bright galaxies. Their existence tells us that matter did not collapse everywhere equally. Some regions became dense, others became drained. This gives the cosmic web its foam-like shape. Dense regions pull matter from less dense regions. Over time, gravity amplifies the difference. The rich become richer. The empty become emptier. Matter flows toward filaments and clusters, while voids expand in relative emptiness. Galaxies do not fill the universe evenly because the early universe itself contained tiny differences in density. Those tiny differences were enough. That is the next strange step in the story. The cosmic web did not appear suddenly after galaxies formed. Its roots go back to the earliest measurable pattern in the universe. The cosmic microwave background, the ancient afterglow from the young universe, is almost perfectly smooth, but not completely. It contains tiny temperature differences, small variations that reflect slightly denser and less dense regions in the early cosmos. At the time, there were no galaxies, no stars, no planets, no Milky Way. There was hot plasma, radiation, dark matter, and the seeds of future structure. Those seeds were extremely small, yet gravity had patience. The denser regions pulled in more matter. The less dense regions fell behind. Dark matter, which does not interact with light the way ordinary matter does, began forming the invisible framework. Ordinary gas later fell into those gravitational wells. Stars formed in galaxies. Galaxies gathered into groups. Groups assembled into clusters. Clusters connected along filaments. The cosmic web is what happens when tiny early differences are given billions of years. This is one of the deepest facts in cosmology. The largest visible structures in the universe may have begun as almost unbelievably small differences in the early universe. A slight excess here, a slight deficit there. Then, gravity, time, and expansion turned those differences into the map of everything. The web is not random decoration. It is a fossil of the universe's beginning, grown to enormous scale. This also means the cosmic web is a record of dark matter. Without dark matter, the structure we see would be difficult to form in the time available. Ordinary matter was tightly coupled to radiation in the early universe, but dark matter could begin gathering gravitationally earlier. It provided the deep wells into which gas eventually fell. In simulations, dark matter naturally forms a web-like pattern under gravity: clumps, sheets, filaments, and voids. Galaxies form where the conditions allow matter to cool and collapse inside that framework. So when we look at galaxy surveys, we are looking at light, but we are also indirectly seeing the shape of something dark. This is why the cosmic web is not just large, it is partly invisible by nature. Imagine walking through a city at night, where only a few streetlights are on. You can see the lamps, and from their arrangement, you infer the roads. But the roads themselves may be dark. Some neighborhoods may be barely lit. Bridges may exist where no light is visible. From above, the glowing points reveal a structure, but not the whole structure. Galaxies are the streetlights. Dark matter is much of the road system. Hot gas and faint gas are the mist between them. Gravity is the rule that connects the whole map. On smaller scales, gravity builds stars, planets, moons, rings, and solar systems. On larger scales, it builds clusters and filaments. But the web also carries the influence of cosmic expansion. Space itself expands, pulling distant structures apart, while gravity tries to pull matter together. The shape we see is the result of this long competition. Inside dense regions, gravity can win locally. Galaxies bind into clusters. Stars orbit galactic centers. Clusters hold hot gas. Dark matter halos keep structures together. Across larger distances, expansion dominates. The web grows, stretches, and evolves. Distant regions move away from one another. In the far future, accelerating expansion may isolate gravitationally bound neighborhoods, making the larger web harder and harder for future observers to see. So, the cosmic web is not only a map of where matter is, it is also a map of what gravity managed to build before expansion separated the stage too much. That is why it matters for the fate of the universe. But before we go that far, we need to understand what the web looks like from inside one of its strands, because we are not outside it. We are inside it, and our position shapes everything we see. The Milky Way belongs to a cosmic neighborhood that is not randomly placed. Our galaxy, Andromeda, and their companion galaxies sit within a gravitational environment connected to larger flows. The local group is moving through space. Nearby structures influence that motion. The galaxies around us are arranged in patterns that connect to the broader large-scale structure. From Earth, the cosmic web is not visible as lines painted on the sky. Instead, we detect its presence by looking outward in many directions and measuring how galaxies are distributed. In one direction, we see concentrations. In another, emptier regions. Some directions are blocked by the dust and stars of the Milky Way itself, which creates a zone where distant galaxies are harder to observe. Our own galaxy gets in the way of seeing the larger one. This is a strange limitation. To map the universe, we first have to look through the object we live inside. The Milky Way is both our home and our foreground obstruction. That means our cosmic address had to be reconstructed carefully. Astronomers use many wavelengths of light. Infrared can peer through dust better than visible light. Radio observations reveal gas. X-ray observations show hot gas in clusters. Gravitational lensing reveals mass, even when it is dark. Each method adds a layer to the map. The web is not discovered once. It is uncovered repeatedly through different kinds of evidence. Galaxy redshift surveys show the bright traces. Weak gravitational lensing shows how mass bends the light of background galaxies. X-ray and radio observations can reveal hot gas in clusters, and sometimes material between them. The cosmic microwave background gives the starting conditions. Computer simulations test whether gravity and dark matter can grow the structures we see. When all of these lines of evidence point toward a web-like universe, the pattern becomes much harder to dismiss as an illusion. And yet, the scale still feels almost impossible. Consider a filament. A filament in the cosmic web is not like a rope you could see from a spacecraft window. It may be millions of light years thick and hundreds of millions of light years long. It may contain galaxy groups, gas, dark matter, and clusters strung along its length. If you were inside one, it would not feel like being inside a tunnel. The distances between galaxies would still be enormous. The stars would still look isolated. Space would still feel mostly empty. Only from far away, with enough data, would the filament become visible as a structure. This is one of the reasons the cosmic web is hard to imagine. It is not dense in a human sense. Even its crowded regions are almost unimaginably empty by everyday standards. A galaxy cluster can contain thousands of galaxies, but the space between those galaxies is still vast. A filament can connect clusters, but it is not a solid bridge. It is a statistical and gravitational structure, a real concentration of matter spread across terrifying distances. The universe can be structured and empty at the same time. That contradiction is at the heart of the cosmic web. The web is enormous, but thin, connected but sparse, real, but not something a human body would ever touch as an object. If a spacecraft traveled through a filament, it would still spend nearly all its time in darkness. It would not pass stars like city lights along a road. It would cross distances so large that the local density would mean little to its passengers. The web is not built for travelers. It is built for maps. At the same time, it controls where travelers could ever find galaxies. If a civilization wanted to expand across the universe, the web would be its geography. Dense nodes would be attractive because they contain many galaxies within a relatively smaller cosmic region. Filaments would act as the broad routes, where galaxies are more common. Voids would be deserts, not because they contain absolutely nothing, but because their distances between useful stops would be far worse. This turns the cosmic web into a kind of cosmic terrain. Not terrain made of ground, but terrain made of probability. Where are galaxies likely to be? Where are resources concentrated? Where are stars rare? Where would signals pass through emptiness for longer? Where could gravitational structures remain bound? Where does expansion make the next destination fade beyond reach? The cosmic web is not only beautiful, it is practical, if any future intelligence ever thinks on intergalactic scales. But for us, it is first a warning about scale. Our maps are still small compared with the whole observable universe. The observable universe itself may be only a portion of the full universe. And the cosmic web we trace is limited by how far light has reached us, how bright galaxies are, how well we can measure them, and how much of the sky our surveys cover. Every map is a window, not the whole room. That is why new missions matter. ESA's Euclid mission, for example, is designed to map the large-scale structure of the universe across space and time by observing billions of galaxies, helping scientists study dark matter and dark energy. Wide surveys do not just give prettier pictures. They improve the three-dimensional census of the cosmic web. They help reveal how structure formed and how it changed over billions of years. Each new survey is like turning on more lights in the cosmic city. But even with billions of galaxies, the map remains incomplete. Some galaxies are too faint. Some are too distant. Some are hidden behind dust. Some are seen as they were billions of years ago, not as they are now. Some structures are inferred through gravity rather than direct brightness. And the web beyond the observable horizon cannot be mapped by us at all. This means that the cosmic web is bigger than we can imagine in two different ways. It is bigger physically, because the structures extend across hundreds of millions or billions of light years. And it is bigger epistemologically, because our knowledge only covers what light and gravity allow us to measure. The mind tries to make the web into an object, but it is also a boundary of knowing. This is why the title is not only about size, it is about the fact that the largest structure we can describe may still be only the local visible portion of a deeper pattern. To see how this pattern formed, we need to go back again, before galaxies, before clusters, before the first filaments became luminous, to the period when the universe was almost smooth. Almost smooth is the key. If the young universe had been perfectly smooth, gravity would have had no preferred places to build. Matter would have remained evenly spread, and no stars or galaxies would have formed in the way we know. If the early universe had been too clumpy, structure might have collapsed too violently, perhaps producing a universe very different from ours. Instead, the early universe had small variations. Those variations became everything. The cosmic microwave background shows those early irregularities as tiny temperature differences. They are not dramatic to look at, but they are the beginning of cosmic architecture. They mark places where density was slightly higher or lower. Dark matter responded gravitationally. Matter fell inward, voids emptied, filaments thickened, nodes became clusters. In this sense, the cosmic web is an ancient amplification. It is the universe turning whispers into continents. The first stars formed inside the densest early regions. Their light changed the universe. Galaxies assembled through mergers and accretion. Gas flowed along filaments into growing halos. Clusters developed at intersections where streams met. The web became more pronounced as cosmic time passed. But the web was never only made of galaxies. Between galaxies lies gas, and some of that gas is extremely important. Astronomers have long searched for missing ordinary matter, baryons that should exist according to cosmological measurements, but are hard to detect because they are spread thinly through intergalactic space. Some of this material is believed to reside in warm hot gas along filaments, difficult to see directly because it is too diffuse and not bright like stars. This hidden gas makes the web more physical. It is not just a map of galaxy points. It includes reservoirs of matter between galaxies. It feeds galaxies. It can be heated by shocks and feedback. It can connect clusters. It can carry clues about how ordinary matter moved from the early universe into the structures we see. The web is not empty decoration around galaxies. In many ways, galaxies are the condensed highlights of the web. They are where gas cooled enough and gravity concentrated enough to make stars. Around them lies a much wider environment that affects their growth. A galaxy inside a dense region may experience mergers, tidal interactions, gas stripping, and cluster processes. A galaxy in a quieter filament may have a different history. A galaxy inside a void may evolve with fewer major encounters. Cosmic address matters. A galaxy is not only what it is internally, it is also where it lives in the web. This is true for the Milky Way as well. Our galaxy's future is shaped partly by local gravity, especially Andromeda and the local group. But our larger environment also determines what is nearby, what is moving with us, and what may eventually remain gravitationally connected. The cosmic web is the background architecture behind the story of our galaxy. And yet, from Earth, none of this is obvious. A child can look at the night sky and see scattered stars. A camera can see the Milky Way as a glowing band. A telescope can see galaxies beyond. But the web requires measurement, patience, and abstraction. It is one of those truths that is not hidden because it is small, but because it is too large to fit into direct perception. No human eye can step back far enough. No spacecraft can fly outside the observable universe and take a photograph. No civilization can wait casually for light from beyond the horizon. We must infer the largest pattern from inside it. This makes the cosmic web similar to living inside a single cell and trying to map the whole body. The cell has clues. Signals pass through it. Structures connect to it. Forces shape it. But the full organism is beyond local experience. We are inside the universe's structure, using light from ancient sources to reconstruct the shape of the structure itself. That is why the cosmic web feels both scientific and unsettling. It is not a fantasy. It is measured. It is simulated. It is predicted by our best models of structure formation, but it also forces a change in perspective. Galaxies become smaller. Clusters become local features. Superclusters become regions in a wider pattern. Even the Milky Way becomes a single ordinary node in a vast gravitational network. The web does not care about human scale. It was forming before Earth existed. It will continue evolving after Earth becomes unrecognizable. Its largest threads are older than the Sun, wider than civilizations can cross, and shaped by matter we cannot directly see. To understand it better, imagine one of its nodes, a galaxy cluster. A cluster is not just a pile of galaxies. It includes dark matter, hot gas, and many galaxies moving under gravity. The hot intracluster gas can emit X-rays. The total mass can bend background light through gravitational lensing. The galaxies themselves are only part of the mass budget. Much of the cluster's gravity comes from dark matter, and much of its ordinary matter may be in hot gas rather than stars. Clusters sit at intersections of filaments because matter has flowed there for billions of years. They are cosmic cities at highway crossings. Galaxies fall into them along filaments. Groups merge. Gas is shocked and heated. Star formation can be altered. Spiral galaxies can lose gas and become quieter. Massive elliptical galaxies can grow through mergers near the center. Black holes can influence surrounding gas. The cluster becomes a record of many journeys converging. Now zoom out again. The cluster itself is only one knot. Several filaments may connect to it. Beyond those filaments are other clusters. Between them are voids. Some walls stretch like broad membranes. Some regions form supercluster-scale patterns. The names humans give these structures help us talk about them, but the physical web is continuous and complex. This complexity is important because it prevents the universe from being simply divided into stuff and empty space. The web is not just stuff in one place and nothing elsewhere. It is a gradient of density. Matter becomes concentrated, but not absolutely. Voids have matter, but far less. Filaments are not solid but denser. Clusters are not isolated but connected. Everything exists inside a landscape of relative density. This is also why computer simulations are so powerful. In simulations, scientists can start with early universe conditions and let gravity evolve matter forward. Dark matter particles gather into halos, filaments form, voids expand, clusters develop at intersections. The simulated universe begins to look like the observed one. When simulations match surveys, they support the idea that we understand the broad ingredients: early density fluctuations, dark matter, ordinary matter, gravity, expansion, and dark energy. But simulations also reveal how much is happening beyond what telescopes easily show. They show dark matter filaments that cannot be photographed directly. They show gas flows too faint to see. They show mergers over timescales too long to observe in real time. They show how a galaxy's environment influences its fate. A simulation is not the universe, but it can make the hidden architecture visible. The cosmic web is therefore both observed and modeled. It is seen through galaxies, felt through gravity, reconstructed through maps, explored through simulations, tested by missions designed to measure structure across enormous volumes. This layered evidence is why the concept is so central to modern cosmology. But the truly frightening part is not only that the web is huge, it is that the web may be the largest structure any intelligence inside our universe can ever meaningfully map. And even then, only partially. The observable universe has a horizon. We cannot see beyond the distance from which light has had time to reach us. Because the universe has a finite age and space expands, there are limits to observation. The cosmic web beyond that horizon may continue, but it is causally hidden from us. No telescope can collect light that has not arrived. No patience can overcome certain horizons, if expansion prevents new information from ever reaching us. So when we say the cosmic web is bigger than we can imagine, we are also admitting that our maps may end before the web does. The pattern might continue beyond sight. It might repeat. It might change. It might be part of a universe far larger than the observable portion. We can test what we can see, but the total scale may remain unknown. This uncertainty gives the cosmic web a strange emotional weight. It is not simply large. Large still sounds measurable. A mountain is large. A planet is large. A star is large. A galaxy is enormous, but we can still name its diameter. The cosmic web is different because its scale is tied to the limits of observation itself. It is the structure of everything we can map, and possibly only a visible fragment of everything that exists. To continue, we need to look at one of the most important features of the web, the voids. Because the web is not made only by what gathers, it is also made by what is missing. A cosmic void can be almost more difficult to understand than a cluster. A cluster is impressive because it contains many galaxies. A void is impressive because it does not. It can be so large that entire regions of the universe appear nearly empty compared with the walls and filaments around them. But a void is not a perfect vacuum. It can contain dark matter, thin gas, dwarf galaxies, and faint structures. It is empty only compared with the denser regions of the web. Yet, that relative emptiness matters. It changes how galaxies form there. It changes the local gravitational environment. It shows how matter drained out of underdense regions over cosmic time. The voids are the dark chambers between the glowing threads. They help give the web its shape. Imagine soap bubbles pressed together. The material gathers along the edges and surfaces, while the interiors are comparatively empty. This analogy is imperfect, but it captures something true. The cosmic web has a foam-like quality. Matter outlines boundaries around vast, low-density volumes. From far away, clusters and filaments look like the bright edges of enormous bubbles. The voids are not failures of structure. They are part of the structure. This matters because voids can be enormous. Crossing one would not feel like flying through a wall of danger. It would feel like nothing happening for an almost unbearable amount of time. No nearby galaxies, few bright landmarks, little chance of convenient resources, darkness, distance, and silence. For any future civilization, voids would be the deep deserts of the universe. Even if faster spacecraft existed, the web would still shape the routes. Traveling along filaments would offer more galaxies, more stars, more potential stops. Crossing voids would demand greater endurance. The map of the cosmic web would become the map of possibility. But humans are nowhere near such travel. For us, the web is not a route yet. It is a revelation. It tells us that the universe has structure on scales we cannot inhabit, that our galaxy is part of a larger pattern, and that what looks empty may be one side of a gravitational story billions of years old. The next layer is even stranger. The web is growing older. It is not frozen forever. Galaxies continue to move. Clusters continue to merge. Gas continues to fall. Heat and cool. Voids continue changing. But the universe's expansion, driven by dark energy, affects the future of large-scale structure. Structures that are gravitationally bound can remain together, but regions not bound to one another will drift apart faster and faster over immense time. That means the cosmic web has a future. It may become less visible to observers in the far future. Distant galaxies will redshift away. Light from beyond certain horizons will never arrive. Future beings in a gravitationally bound remnant might see a much emptier universe, not because the web never existed, but because expansion has hidden much of it from view. This gives the cosmic web a tragic quality. We live at a time when the large-scale universe is still visible. The cosmic microwave background can still be measured. Distant galaxies can still be mapped. The web can still be traced. In the far future, much of this evidence may fade. Cosmology itself may become harder. The universe may not only be larger than we imagine, it may also be more available to us now than it will be to anyone living in the distant future. This makes our era special, not because humanity is central, but because the universe is still readable. The web is still written in light. The question is how far we can read before the pages disappear. For part 1, the most important fact is this: the cosmic web is not a poetic metaphor. It is the actual large-scale arrangement of matter in the universe. Galaxies, clusters, walls, filaments, voids, dark matter, and gas form a structure so large that no single galaxy can represent it, and no human intuition can easily hold it. The Milky Way is inside it. Andromeda is inside it. The local group is inside it. The Virgo region is part of a larger environment. The cosmic microwave background contains the early seeds that grew into it. Dark matter helped shape it. Gravity spent billions of years building it. Expansion now helps decide how much of it can remain connected and visible. And this is only the beginning of the problem. Because once we understand that the universe has a web, we have to ask what the web is doing. Is it still growing? Where does matter flow? How do galaxies travel through it? How does dark energy change it? Could there be structures even larger than the ones we have named? And if the cosmic web is the largest map we can draw, what happens when the map itself begins to vanish beyond the horizon? That is where the second half of the journey begins. Not with a single galaxy, not with a single cluster, but with the dark spaces between them, and the question of whether the cosmic web is only the visible surface of something far larger than the observable universe itself. One way to make this less abstract is to imagine the cosmic web as a map that changes depending on what kind of light you use. With visible light, you see stars and galaxies. The brightest regions stand out first: spirals, ellipticals, clusters, arcs of galaxies, and distant points too faint for ordinary eyes. This view is beautiful, but it is biased toward what shines. With infrared light, dusty regions become less opaque. Galaxies hidden behind the Milky Way's dusty plain can be studied more clearly. Older stars glow through clouds that visible light cannot cross easily. Suddenly, parts of the map that look blank begin to fill in. With radio waves, cold hydrogen and other gas can appear. Radio surveys can reveal structures that are not obvious in starlight alone. They can show how gas extends beyond the bright edges of galaxies and how material may connect systems across larger regions. With X-rays, the hottest gas becomes visible. Galaxy clusters often contain enormous amounts of extremely hot gas, heated to such high temperatures that it glows in X-rays. This gas is not a small detail. In clusters, much of the ordinary matter is not locked inside stars. It is spread through the space between galaxies. With gravitational lensing, even darkness leaves a mark. Mass bends the path of light. When background galaxies appear slightly distorted, astronomers can use those distortions to infer where mass lies. This method is especially important because dark matter does not glow, but it still has gravity. Lensing lets scientists map mass in places where light alone would give an incomplete picture. The result is not one simple image. It is a stack of evidence. Each wavelength shows a different layer. Each survey fills a different gap. Each technique corrects a different human limitation. The cosmic web is too large and too subtle to be captured by one kind of observation, so astronomers have to approach it like investigators reconstructing a city from lights, shadows, heat, motion, and the bending of distant signals. This is also why the web keeps becoming more detailed. The early maps showed that galaxies were clumpy. Later maps revealed filaments and walls. Newer surveys measure millions of objects. Future maps aim to trace billions. The web is not suddenly changing because the universe decided to become more complex. It is changing in our understanding because our tools are improving. The structure was already there. We are only learning how to see it. And the more we see, the less isolated anything appears. A galaxy may look alone in a photograph, floating against blackness. But in a full cosmic map, that galaxy has an environment. It may sit inside a group, at the edge of a filament, near a void, or inside the outskirts of a cluster. It may be falling toward a larger structure. It may be losing gas because of its surroundings. It may be receiving fresh gas along a filament. It may be shaped by mergers that happened because the web guided other galaxies into its path. This means the cosmic web is not just background scenery. It helps write the lives of galaxies. A galaxy in a crowded cluster can be transformed by encounters, tidal forces, and hot gas. A galaxy in a filament may continue receiving cold material that fuels star formation. A galaxy near a void may evolve slowly, with fewer collisions. The same basic laws of physics apply everywhere. But the neighborhood changes the story. The Milky Way has its own story inside this pattern. It grew by absorbing smaller systems. It carries stellar streams, evidence of past mergers. It is approaching Andromeda under gravity, and both galaxies are embedded in a larger dark matter environment. Even our future collision with Andromeda is not an isolated drama between two galaxies. It is part of the local group's longer history inside the wider web. From a human point of view, the Milky Way feels like the entire stage. From the web's point of view, it is one moving spark. Another way to understand the scale is to compare ordinary cosmic distances with web distances. The distance from Earth to the Moon is about 1¼ light seconds. The distance from Earth to the Sun is about 8 light minutes. The nearest star system is a little over 4 light years away. The Milky Way itself is roughly 100,000 light years across. These numbers already feel impossible. But the cosmic web operates beyond them. The distance to Andromeda is millions of light years. The distance to the Virgo cluster is tens of millions. Large filaments and walls can stretch for hundreds of millions. The observable universe reaches across tens of billions of light years in every direction. On that scale, the Milky Way is not only small, it is barely a punctuation mark. This is not said to make Earth feel meaningless. It is said because scale changes the kind of story being told. A planet is about surfaces, climates, oceans, and atmospheres. A solar system is about orbits, stars, small bodies, radiation, and time. A galaxy is about stellar populations, dark matter halos, spiral arms, black holes, and mergers. The cosmic web is about distribution itself, where matter ended up after billions of years of gravitational growth. It is not a place inside the universe. It is the arrangement of the universe at the largest visible level. That is why the web feels different from other space topics. You can imagine standing on Mars. You can imagine flying past Saturn. You can picture a black hole. Even if the physics is extreme, you can show a galaxy in one frame. But the cosmic web does not fit into a frame. Any image that shows it must compress reality so brutally that galaxies become dots and hundreds of millions of light years become lines on a screen. The image may be accurate as a map, but it hides the experiential truth. Each dot is an entire galaxy, and every gap is a distance so large that a beam of light needs longer than human civilization has existed many times over just to cross it. This is where the web becomes terrifying in a quiet way. It is not terrifying because it attacks us. It is terrifying because it reveals what kind of structure we belong to. We live on a planet inside a solar system, inside a galaxy, inside a group, inside a larger gravitational landscape, inside a web that stretches across the observable universe. Each level is real. Each level is larger than the last, by a scale that makes the previous one seem almost local. The web is the final visible level before our language begins to break. There may be larger arrangements, depending on how one defines structure and on what future surveys confirm. There are named walls, superclusters, and enormous associations of galaxies. Some proposed structures push the limits of what cosmology expects to be meaningfully bound or coherent. Astronomers must be careful here, because an apparent pattern can sometimes be a line of sight effect, a survey limitation, or a statistical feature rather than a single physical object in the everyday sense. This caution matters. Not every huge pattern is a single thing. The universe can contain alignments that look dramatic without being bound together, like a planet or a galaxy. The expansion of space changes what can remain connected. Gravity can bind smaller structures, but over enormous scales, apparent structures may be parts of a broader distribution rather than objects with a shared fate. So when we talk about the largest structures, we have to separate three ideas. There is what is visually connected on a map. There is what is gravitationally bound. And there is what belongs to the same statistical pattern of the cosmic web. These are not always the same. A galaxy cluster can be bound. A local group can be bound. A filament may guide matter and connect regions, but not every part of a long filament is necessarily bound together forever. A supercluster can describe a large region of related structure, but accelerating expansion may still separate its parts over time. The cosmic web is therefore not a solid net holding everything together permanently. It is a pattern of matter shaped by gravity within an expanding universe. That distinction prevents the script from becoming simple fantasy. The web is real, but it is not a steel cage. It is a cosmic arrangement, evolving under competing forces. This also means the web is different depending on when you observe it. In the early universe, the web was only a set of density seeds, invisible as galaxies. Later, as matter collapsed, the first luminous structures appeared. Over billions of years, galaxies filled the web more clearly. At our time, the web can be mapped through galaxy surveys and other methods. Far in the future, accelerated expansion may isolate bound regions and remove distant structures from view. The cosmic web has a past, a present, and a future. Part of the second half of this journey will follow that timeline more deeply. For now, it is enough to see that the web is not only a spatial structure, it is also a historical structure. It tells us how the early universe became the present universe. It records the growth of density. It marks where gravity succeeded, where matter drained away, where galaxies formed, and where emptiness widened. If you could pause the universe and see all its mass at once, the web would be the shape of that history. But because we cannot pause the universe, our view is more complicated. Looking far away is also looking back in time. The distant web is younger than the nearby web as we observe it. A galaxy seen 10 billion light-years away is not being seen as it is today. It is being seen as it was when its light began the journey. This means our three-dimensional maps are also time maps. The farther we look, the earlier the universe appears. So the cosmic web we map is not one frozen present moment. It is a light cone view, a layered record of different cosmic ages. Nearby structures show the relatively recent universe. Distant structures show younger stages. The cosmic microwave background shows the seed pattern before galaxies existed. The map is therefore not only spatially vast, but temporally deep. That makes interpretation harder. When astronomers compare the nearby and distant web, they are not simply comparing two regions. They are comparing different times in cosmic history. This is exactly what makes large surveys powerful. They can show how structure evolved across time, how galaxies changed, how dark energy affected expansion, and how dark matter guided formation. The cosmic web is a time machine built from distance. Every filament in a deep survey is also a message from the past. Every distant cluster is a younger version of cosmic structure. Every void seen far away is a record of how emptiness developed in a different era. The web is bigger than we can imagine because it is not only wide, it is old in every direction. When you look into it, you look through the history of structure itself. This is why the cosmic web is one of the most important ideas for a channel about the universe as a whole. It connects almost every major cosmic subject. Dark matter shapes it. Dark energy changes its future. The Big Bang leaves its initial pattern. Galaxies form within it. Black holes grow inside galaxies inside its nodes and filaments. The fate of future civilizations would be limited by its geography. The visible universe becomes understandable only when the web is seen as the large-scale framework. Without the web, galaxies are islands. With the web, galaxies become parts of a continent made of gravity, and that continent is still being mapped. There is one more reason Part 1 needs to end here, at the edge of the voids and the beginning of the flows. The web is not just a picture of where matter is located, it is also a picture of motion. Galaxies are not pinned to their places like beads glued to a board. They move. Groups fall inward, clusters merge, voids expand relative to the dense walls around them. Matter streams along filaments. The entire structure has a dynamic life. If we only imagine the cosmic web as a static image, we miss half the truth. It is not a frozen spiderweb. It is more like a slow cosmic river system, with galaxies as bright foam carried by dark currents. The second half has to follow those currents. It has to move from map to motion, from structure to fate, from the visible threads to the hidden forces that may decide what the universe becomes next. Because the cosmic web is not finished. It is still changing. And the more we map it, the more it looks like the universe is not merely filled with objects. It is organized around connections too large for any one object to understand. That idea may be the most important bridge into the next part. A connection in the cosmic web does not mean a road a spacecraft could easily follow. It means a relationship written in density, gravity, history, and motion. A filament can connect clusters without making the journey between them. Simple. A wall can contain thousands of galaxies without making them close in any human sense. A void can look almost empty while still containing dark matter and thin gas. Everything depends on scale. This is the trap the mind falls into again and again. When we hear the word web, we imagine threads close enough to touch. But the cosmic web is made from distances so large that even its connections are oceans. A strand can be real and still be almost impossibly empty. A node can be crowded and still contain far more darkness than stars. A map can show structure while hiding the loneliness inside each part of that structure. That is why the cosmic web is bigger than a simple map can show. A map gives shape. It does not give duration. It does not show how long light takes to cross a single gap. It does not show how a galaxy experiences billions of years of falling, merging, heating, stripping, and rebuilding. It does not show how many generations of stars can rise and die while a signal travels from one large structure to another. The web is not only large in distance, it is large in consequence. It decides where galaxies are common and where they are rare. It affects how gas moves into galaxies. It shapes where clusters grow. It preserves traces of the early universe. It hides dark matter in plain sight through gravity. It marks the border between cosmic neighborhoods that may remain connected and regions that expansion will eventually remove from reach. So if Part 1 has one clear answer, it is this: The cosmic web is not a thing beyond galaxies. It is the pattern that makes galaxies part of something larger. It is the universe at the scale where individual objects stop being the main story. From here, the next question becomes unavoidable. If the cosmic web is the largest structure we can map, then what is it telling us about the future? Will its filaments keep feeding galaxies? Will its voids keep widening? Will its clusters become isolated islands as dark energy stretches the space between them? Will future astronomers still be able to see the web? Or will the evidence fade until the universe looks smaller than it truly is? And if our observable cosmic web is only one visible patch of a much greater universe, how much of reality will always remain outside the map? That is where the second half must go. Not deeper into one galaxy, not toward one planet or one star, but outward through the filaments, into the voids, and into the future of the largest pattern the universe has ever allowed us to see. Outward, the first thing the web teaches is that the future is not evenly distributed. A galaxy inside a dense knot does not face the same future as a galaxy alone inside a void. A cluster buried at the meeting point of several filaments does not age like a small spiral drifting near the edge of an empty region. Even on the largest scales, location matters. The universe is not a smooth ocean of galaxies sprinkled randomly through darkness. It is a landscape, and the landscape changes what can happen next. Imagine pulling back from the Milky Way until our galaxy becomes only one pale spiral among many. The first pattern you notice is local. Andromeda sits nearby on cosmic scales. Smaller galaxies drift around both of them. The local group becomes a small island of gravity. Pull back farther, and the island joins longer rivers of galaxies. Pull back again, and those rivers bend toward clusters, away from voids, and through long corridors that can stretch for hundreds of millions of light years. That is where the second half begins, not by asking what the web looks like, but by asking what the web does. It feeds galaxies, it starves galaxies, it guides motion, it hides matter, it builds clusters, it opens voids. It remembers the early universe in a way no single galaxy can. It also points toward a future where the largest pattern we can map may slowly become harder to see. Start with the feeding. A galaxy is not a closed machine. It is not born with all the gas it will ever use, then simply burns until the tank is empty. Galaxies grow by taking in material from their surroundings. Some of that material arrives through mergers, when smaller galaxies fall in and become part of a larger system. But some arrives more quietly along the large-scale environment itself. Gas does not fall equally from every direction. It often follows the same cosmic lanes traced by dark matter and galaxies. This is one reason the web matters. It is not only a map of where galaxies already are, it is also a map of where matter has been able to flow. Near a filament, a galaxy may receive fresh material for long periods of time. That gas can settle, cool, and eventually help form new stars. Near the center of a rich cluster, the story can change. A galaxy entering a cluster may run into hot, thin gas spread through the cluster environment. Its own gas can be stripped away. Star formation can slow. A spiral full of blue young stars can gradually become a quieter system with less fuel. So the web is not simply decorative, it changes the life cycle of galaxies. A galaxy inside a filament may be part of a slow traffic system. A galaxy falling into a cluster may be entering a crowded gravitational city where encounters become more common and gas becomes harder to keep. A galaxy deep inside a void may live a quieter, more isolated life, with fewer neighbors, fewer mergers, and fewer fresh supplies. This means that when we look at the night sky, every galaxy carries the mark of its address. The Milky Way is not only the Milky Way because of its stars, it is the Milky Way because of where it formed, what it merged with, what it avoided, What kind of dark matter halo grew around it, and what larger flows surrounded it over billions of years. Its future is not written only inside its disk, it is also written in the wider structure around it. That wider structure can be difficult to feel, because human minds are trained to understand objects. A planet is an object. A moon is an object. A star is an object. Even a galaxy can be imagined as one object if we stand far enough away from it. But a filament is different. A void is different. A supercluster is different. These are not objects with hard surfaces. They are regions of density, motion, and gravity. Their edges are not walls. Their borders are defined by flows, by probabilities, by maps made from millions of points. That makes them harder to picture. It also makes them more powerful. Because if the universe is a web, then the largest things in existence are not solid things at all. They are relationships between matter across distances so vast that light itself needs ages of cosmic history to cross them. The next question is, what happens to those relationships as the universe grows older? For much of cosmic history, gravity had time to pull matter into denser and denser structures. Tiny unevenness in the early universe became clouds. Clouds became the places where galaxies formed. Galaxies gathered into groups. Groups fell along filaments. Clusters formed at intersections. The web sharpened, like a faint sketch gradually darkened by billions of years of gravity. But expansion was always happening too. At first, gravity could compete effectively on many scales. Matter attracted matter, and dense regions became denser. Voids lost material to their surroundings and became emptier. The web became more distinct. Then dark energy began to dominate the large-scale behavior of the universe, and the expansion of space started accelerating. This does not tear apart galaxies. It does not pull the solar system open. It does not break atoms. Bound structures can remain bound. The Milky Way will not expand because space between its stars expands. A galaxy cluster that is truly gravitationally bound can stay together. But the web is not all equally bound. Some parts are already committed to staying together. Other parts are only neighbors for now. Galaxies that seem to share the same large pattern may not remain connected forever. A filament can be visually part of one grand structure, while sections of it are drifting into futures that no signal can cross. This is where the cosmic web becomes more than a structure. It becomes a clock. The web we see is a record of the past, a map of the present, and a warning about the future. It shows where gravity has organized matter. It also shows where expansion is beginning to separate what gravity has not permanently captured. The great voids are the clearest example. A void is not empty in the perfect sense. There can be galaxies inside it. There can be gas, dark matter, faint dwarfs, and invisible particles passing through. But compared with filaments and clusters, a void contains very little. If a dense node is a crowded city, a void is a continent of night between cities. As time passes, voids tend to expand in relative importance. Matter flows out of low-density regions toward higher-density regions. Galaxies become more concentrated along the web. The empty regions become emptier by comparison. In a universe with accelerating expansion, those empty distances also become more permanent. Imagine a future astronomer living in a galaxy inside a small bound group long after the present age. Their sky may still contain local stars. Their home galaxy may still have structure, but the broader cosmic web could be far harder to detect. Distant galaxies will have redshifted away. Their light will stretch, fade, and eventually become unreachable to ordinary observation. The grand pattern that we can map now may become a forgotten truth, visible only through ancient records if any records survive. That possibility is unsettling for a simple reason. We live during a period when the universe still shows us enough of its structure to understand that structure exists. Too early, and the web had not fully formed. Too late, and much of it may be hidden beyond the horizon. Our moment is temporary. It is not only the stars that will change. It is the evidence. The cosmic web is enormous, but it is also time-sensitive. It can be studied because light from many different distances still reaches us. We can compare young galaxies with older galaxies. We can measure redshifts. We can map clusters and voids. We can use gravitational lensing to infer dark matter. We can use the cosmic microwave background as a starting pattern, then compare it with the present-day universe. Future observers may not have all of those tools. They might live inside a quiet, merged galaxy, surrounded by darkness that contains little visible evidence of anything beyond their local gravitational island. The rest of the cosmic web could still exist, but not as something available to them. In that future, the universe may look smaller than it is, not because it has become small, but because the light from its largest structure no longer arrives. This is one of the strangest lessons hidden inside the web. A universe can become harder to understand with time. That does not happen because intelligence fades automatically. It happens because information has a horizon. Observations depend on what light can reach you, and the expansion of space changes that answer. The web is not only out there, it is visible now. The word now matters. To understand how large the web really is, we have to move from the future back to the present and ask what the biggest mapped structures actually are. Galaxy surveys do not see the universe all at once. They build maps gradually, by measuring the positions and redshifts of enormous numbers of galaxies. Each redshift gives a clue to distance. Each galaxy becomes one point in a three-dimensional structure. With enough points, the pattern appears. At first, the points look messy. Then the eye begins to see chains. The chains become walls. The walls surround voids. Clusters sit at intersections. Superclusters appear as extended regions of greater than average density, though not all of them are gravitationally bound objects in the simple sense. This distinction matters. A galaxy cluster can be a bound structure held together strongly enough that its galaxies share a common gravitational future. A supercluster can be more complicated. It may look like one vast arrangement, but expansion can separate parts of it over time. The name can make it sound like a single object, when in reality it may be a section of the web identified by density and motion. That is why the cosmic web forces us to be careful with language. When people hear the word structure, they imagine something built, a bridge, a tower, a wall. But the largest structures in the universe are not constructed objects. They are patterns created by gravity acting on matter across cosmic time. They have no steel, no surface, no edge where you could place a flag, yet they are real enough to guide galaxies. They are real enough to affect where stars form. They are real enough that their invisible dark matter can bend light from more distant galaxies behind them. They are real enough that missions are built to map them. And the more precisely we map them, the more the universe stops looking like a collection of islands and starts looking like one connected system. But connected does not mean safe. It does not mean simple. It does not mean permanent. A filament can connect clusters across a vast distance while still being mostly empty by human standards. If a spacecraft could somehow cross such a filament, it would not pass through a bright tunnel of stars. It would spend most of its time in darkness. Galaxies might lie along the route, but the spaces between them would still be immense. The cosmic web is dense only compared with the voids around it. Compared with Earth, or even compared with the neighborhood of a star, it is almost nothing. That is another source of its scale. The web is not big because it is packed. It is big because it arranges emptiness. A city on Earth is dense because buildings stand close together. A galaxy is dense because stars share a gravitational system. A cluster is dense because many galaxies occupy one region. But a cosmic filament can be millions of light-years thick and hundreds of millions of light-years long, while remaining thinner than any ordinary idea of matter. It is a skeleton made mostly of absence. And yet that skeleton is where much of the visible universe finds its place. This is why dark matter is central to the story. Ordinary matter can cool, shine, collapse, collide, and form stars. Dark matter does not shine, at least not in any way we have detected. It does not form bright clouds. It does not make planets. It does not announce itself with color. But because it has gravity, it shapes where ordinary matter gathers. In the standard picture, dark matter forms the main gravitational scaffolding of the web. Ordinary matter falls into that scaffolding. Galaxies appear where the conditions allow gas to gather and stars to ignite. So when we map galaxies, we are mapping a luminous trace of a deeper structure. The galaxies are not the whole web. They are lamps hanging on it. This is easy to say, but hard to feel. A galaxy contains hundreds of billions of stars. It seems impossibly large already. Calling it a lamp sounds absurd until the scale changes. On the scale of the cosmic web, even galaxies become points. Entire clusters become knots. Superclusters become regions. The familiar universe becomes texture. That change of scale is not just emotional, it is scientific. It tells us that the most important mass in the structure may not be the mass that glows. If dark matter were not there, the web would not form in the same way. Galaxies would not gather in the same pattern. Clusters would not have the same gravitational strength. Light from background galaxies would not be bent in the same way by invisible mass. The map would be different. So the cosmic web is also a dark matter detector spread across the universe. Every filament is evidence. Every cluster is evidence. Every gravitational lensing pattern is a clue. Every void is part of the same case because voids show where matter did not gather. The universe, on its largest scale, becomes a crime scene of missing mass. Not missing because it is absent, missing because it refuses to shine. This is why new surveys matter so much. A better map of galaxies is not only a better picture, it is a test of cosmology. It can show whether the growth of structure matches what our models predict. It can help measure how dark energy influences expansion. It can reveal whether dark matter behaves as expected. It can show how clusters, filaments, sheets, and voids developed from the early universe to now. A map becomes an experiment, and the experiment is still unfinished. The cosmic web is too large to fit into one telescope image. It must be assembled from many observations, many wavelengths, many distance estimates, and many corrections for selection effects. Some galaxies are bright and easy to see. Others are faint. Dust can hide regions. Distance dims light. Redshift moves light into different parts of the spectrum. Surveys have limits, and those limits shape the maps they produce. That means the cosmic web we draw is both real and incomplete. It is not imaginary. The pattern is not just a trick of the eye, but our picture is always a version built from available data. Better instruments sharpen it. Wider surveys expand it. New methods reveal fainter matter between the bright points. The web grows in our understanding not because it physically grows overnight, but because our map catches up with what was already there. That is an important difference. The universe was not waiting for us to notice it before it became structured. The filaments existed before we named them. The voids were there before we measured them. The clusters were pulling matter inward before any telescope could record the pattern. Our maps are late arrivals. And they are small arrivals compared with the whole. Because even the observable universe may not contain the entire cosmic web. It contains the part whose light has had time to reach us since the beginning of the hot Big Bang. Beyond our horizon, if the universe continues, the pattern may continue too. There may be more filaments, more voids, more clusters, more enormous structures that follow the same physical laws, but remain forever beyond observation. We should be careful here. Science cannot simply describe what cannot be observed as though it has been seen. But the same models that explain the observable universe often allow space to extend beyond the observable part. If that is true, then our cosmic web is not the whole web. It is a visible sample, a patch of a larger fabric. That idea changes the meaning of scale again. When we say the cosmic web is bigger than we can imagine, we are not only saying that the visible web is large, we are saying that the visible web may be only the accessible section of a structure whose full extent is unknown. That does not mean anything mystical has to be added. It means the boundary of observation is not necessarily the boundary of existence. And that may be the most important line in the entire story. A map can end before reality ends. The edge of our observable universe is not a wall where galaxies stop being possible. It is a horizon defined by light, time, and expansion. Beyond it, there may be regions whose light has not reached us, and may never reach us. If the cosmic web continues there, then the largest structure we can discuss scientifically is also part of a larger question we cannot directly answer. That is where the web becomes humbling, without needing exaggeration. It is already too large for the human mind at visible scales. Then, it may extend beyond visibility. It is already mostly dark matter. Then, much of it may lie beyond the horizon. It already changes the fate of galaxies. Then, its unseen continuation may contain histories we will never compare with ours. But even within the observable universe, the web is not just a background. It is the stage on which the future of galaxies will play out. Consider clusters. In a rich cluster, galaxies move through a crowded environment. The space between them is filled with hot gas that can glow in X-rays. Gravity is strong. Collisions and close passes can disturb galaxies. Some galaxies lose gas. Others merge. The cluster becomes a place where the quiet spiral life of a galaxy can be transformed. A cluster is not merely a pile of galaxies. It is an ecosystem. Its dark matter halo dominates the gravity. Its hot intracluster gas records violent history. Its galaxies carry scars from interactions. Its central regions may host giant elliptical galaxies built by mergers over long ages. Its outer regions may still be receiving new members along filaments. So a cluster is like a knot in the web that continues tightening as material falls inward. But there is a limit. As dark energy accelerates expansion, more distant material becomes less likely to join bound systems. Future clusters will not necessarily continue growing from unlimited surroundings. Their supply lines can be cut off by cosmic expansion. The web can still exist as a pattern, but the ability of far regions to influence one another weakens. In that sense, the cosmic web has an active era. There is a time when filaments feed, clusters grow, galaxies migrate, and large-scale structure continues to sharpen. Then, there is a later time when much of that process slows on the larger scales. Bound islands remain. Unbound regions separate. The map becomes less connected in any practical sense, even if old light still tells us how connected it once appeared. The universe does not need to break the web dramatically. It only has to make the distances between its parts less crossable. This is a recurring theme in cosmology. Catastrophe is not always an explosion. Sometimes it is separation. Sometimes it is fading. Sometimes it is the slow loss of contact between things that once belonged to the same map. That is why the cosmic web feels different from a planet, a star, or a black hole. Those objects can have dramatic endings. A star can explode. A planet can be swallowed. A black hole can merge with another black hole and ring space-time itself. But the web changes in a quieter way. Its future is written through motion, expansion, fuel, and horizon. The voids widen. The clusters settle. The filaments stop being supply lines across the grandest distances. The light from distant regions fades into wavelengths that future instruments may never recover. The result is not a universe with no structure. It is a universe where structure becomes local. That phrase sounds small, but it is enormous. Local structure means the part that remains gravitationally connected. It means the galaxies that can still merge, the stars that can still be reached in principle, the matter that remains inside the same bound island. For our region, the local group will eventually become even more important than it already is. The Milky Way and Andromeda are expected to merge in the far future, forming a larger galaxy-like system. Smaller members of the group will share that fate in some way. Beyond that future island, more distant galaxies will recede into darkness. A future civilization inside that merged system may see a sky filled with local stars, but the great web beyond may be nearly gone from practical view. Their universe may look like one island in a dark ocean, even though ancient records would say there was once a vast cosmic web stretching across visible space. Imagine trying to convince them. Imagine showing them an archive from our time. Maps full of filaments, galaxy surveys, clusters, voids, redshift patterns, lensing maps, background radiation. To them, it might look like a message from an impossible age, when the universe was more generous with evidence. They might ask why the sky no longer shows it. The answer would be simple and terrible. Because the universe changed. Not because the web was false, because the light left. This is one reason our era matters. We are not at the center of the universe, but we are living at a time when the universe still displays enough of its large-scale history to be decoded. The cosmic web is readable now. It may not always be readable in the same way. That turns astronomy into preservation. Every survey is not only collecting data for current science, it is preserving a view of the universe that future observers may not have. Every map of the cosmic web is a record of a cosmic phase. Every measurement of dark matter distribution, redshift, baryon acoustic features, galaxy clustering, and weak lensing becomes part of a library against cosmic forgetting. This makes the web feel less like a distant abstraction and more like a temporary message. The universe is showing us its largest visible pattern, while it still can. But to understand the full meaning of that message, we have to ask how the web first became visible at all. The cosmic microwave background is often described as the oldest light we can see. It comes from a time when the universe became transparent enough for light to travel freely. It does not show galaxies. It does not show clusters. It does not show the web in its finished form. Instead, it shows tiny temperature differences, small signs of unevenness in the early universe. Those tiny differences mattered. A slightly denser region had slightly stronger gravity. Over time, it attracted more matter. Dark matter began gathering into halos and larger structures. Ordinary matter followed where it could. The web emerged from amplification. A nearly smooth beginning became a complex universe because gravity had time to work. This is why the web is not random. It is the grown version of early conditions. The CMB is like a seed pattern. The modern cosmic web is the forest that grew from it. That comparison is not perfect, but it helps. A seed does not contain a tiny visible tree, but it contains information that shapes what the tree can become. The early universe did not contain finished galaxies and clusters, but it contained variations that shaped where matter would later gather. The terrifying part is how small the beginning was, compared with the result. Tiny differences became superclusters. Subtle variations became vast voids. Slightly stronger gravity in one region, given billions of years, became a knot where thousands of galaxies could gather. This is the universe teaching us that small unevenness, multiplied by time, can become architecture. It is also why simulations are so important. No human can wait billions of years to watch the web form. Instead, scientists start with initial conditions based on early universe measurements. Then, allow gravity, expansion, dark matter, and ordinary matter to evolve inside computer models. If the simulated universe grows a web like the one we observe, the model gains strength. If it fails, something is missing. Simulations are not replacements for the real universe. They are controlled attempts to understand the rules behind it. In a simulation, the web can be turned, sliced, measured, and compared. Filaments can be tracked. Dark matter halos can merge. Voids can expand. Gas can fall into clusters. Galaxies can form in denser regions. The invisible skeleton becomes something we can study indirectly. But simulations also reveal how sensitive the web is to the ingredients of the universe. Change dark matter, and small-scale structure can change. Change dark energy, and the growth of structure can change. Change the initial spectrum of density variations, and the pattern changes. The web is therefore not only a consequence, it is a test. The universe has written its physics into its geography. That is one of the most powerful ideas in cosmology. If we map the geography well enough, we may learn the physics behind it. This is why the cosmic web connects many of the biggest mysteries at once. Dark matter is there because the web needs invisible gravity to form as it does. Dark energy is there because the future and expansion of the web depend on it. Inflation is there because the early pattern had to come from somewhere. Galaxy formation is there because the bright points trace the invisible structure. The fate of the universe is there because the web will not remain equally connected forever. The cosmic web is not one topic. It is the place where many topics meet. That is also why it is hard to make it feel small. Every time we zoom in, we find galaxies. Every time we zoom out, we find structure. Every time we ask what the structure is made of, we find dark matter. Every time we ask where it is going, we find dark energy. Every time we ask how it began, we return to the first light. A single filament becomes an entrance into the entire history of the universe. But the story also has a practical side. If a civilization ever tried to spread beyond one galaxy, the cosmic web would matter. It would not be a road network in the easy sense. The distances are still brutal. A filament does not make intergalactic travel simple. But compared with a void, a filament contains more galaxies, more potential targets, more matter, and more gravitational islands. If there were ever routes across cosmic structure, they would likely follow the web, because that is where the destinations are. The voids would be the true oceans. Crossing a void would mean crossing a region where targets are sparse, resources are rare, and errors become harder to correct. A mission through a filament might still face millions of years of travel, depending on technology, but at least it moves through a richer environment. A mission into a void moves into absence. This is not science fiction alone. It is a way of understanding what the map means physically. Matter is not evenly available. Galaxies are not evenly spaced. The future is not evenly reachable. The web shapes not only where things are, but where movement would make sense. Even light follows the consequences of the web. Gravity from massive clusters and filaments can bend light from distant galaxies, creating subtle distortions that help reveal the distribution of mass. This weak lensing is one of the key methods for mapping dark matter across large regions. Light becomes a measuring tool. Distorted images become clues. The universe uses its own gravity to show us where the invisible matter is. That is almost poetic. But the mechanism is concrete. Mass curves space-time. Light follows that curvature. If enough distant galaxies are observed behind a region, their tiny statistical distortions can be used to reconstruct the gravitational field in front of them. The result is not a photograph of dark matter. It is a mass map inferred from the way light has been bent. This is one of the closest things we have to seeing the web's skeleton. And it is still difficult. The signals are subtle. The galaxies are faint. The measurements require careful calibration. The maps depend on large numbers of observations. But the reward is enormous. A way to compare luminous matter with total mass, and to see whether the bright galaxy web follows the deeper dark matter web, as theory predicts. That comparison is where some of the deepest questions hide. Does dark matter behave exactly like cold, collisionless matter on all these scales? Are there small deviations? Does dark energy remain constant, or does it change over time? Does gravity itself behave the same way on cosmic scales as it does in smaller systems? Large-scale structure surveys help test these questions not by visiting filaments, but by measuring the pattern they create. The cosmic web is too large to touch, but not too large to question. This is why it belongs on a channel about the whole universe, not just one object inside it. It is the scale where individual astronomy becomes cosmology. A star tells us about fusion. A planet tells us about formation and chemistry. A galaxy tells us about stars, gas, black holes, and dark matter halos. But the cosmic web tells us about the universe as a whole, its beginning, its ingredients, its expansion, and its future. No single galaxy can answer those questions alone. The web can, or at least, it can give us the largest evidence we have. Still, the web is not easy to explain because it has no familiar human equivalent. The nearest images are nervous systems, spider webs, rivers, roots, cities at night, or glowing cracks through darkness. Each image helps for a moment, then fails. A nervous system is too organized. A spider web is too solid. A river system is too flat. A city grid is too planned. The cosmic web was not designed. It did not grow for a purpose. It is the natural result of gravity acting on early unevenness in an expanding universe filled with dark matter and ordinary matter. That is more powerful than design in some ways because no builder was needed. The laws were enough. Given enough time, the universe organized itself into filaments larger than human imagination. Given enough expansion, it may separate those filaments into unreachable histories. That is the double nature of the web. It connects and it divides. It gathers matter into nodes and it empties the voids between them. It reveals the universe's past and it warns us that the future will hide parts of the present. It makes galaxies part of a larger body while reminding us that most of that body is invisible. This is the part where the title becomes literal. The cosmic web is bigger than we can imagine not only because its physical distances are huge, it is bigger because it contains many kinds of size at once. It has spatial size, filaments and voids stretching across millions and hundreds of millions of light years. It has mass size, dark matter halos, clusters, and unseen gravitational scaffolding, holding more mass than the bright galaxies reveal. It has time size, a story beginning with early density variations and extending into a future of isolation. It has information size, a map that contains clues about dark matter, dark energy, inflation, galaxy formation, and the fate of cosmic structure. It has uncertainty size, the possibility that what we observe is only a visible part of a much larger pattern beyond the cosmic horizon. These are not the same kind of size, but together they make the web almost impossible to hold in the mind. A person can imagine a star by thinking of the sun. A person can imagine a galaxy by thinking of a glowing island of stars. But to imagine the cosmic web, the mind has to abandon the idea that the universe is mainly made of objects. It is also made of arrangement. That arrangement is the hidden subject of the night sky. Every star we see belongs to a galaxy. Every galaxy belongs to an environment. Every environment belongs to a larger flow. Every flow is shaped by dark matter and expansion. Every map we draw is one layer of a pattern that began before the first star existed. When we look at the sky from Earth, we do not see the web directly. We see a scatter of stars within our own galaxy. With telescopes, we see more galaxies. With surveys, we see their distribution. With lensing, we infer the dark skeleton. With the cosmic microwave background, we see the early seeds. The web appears only when many kinds of evidence are stacked together. That is why it feels hidden. Not hidden because something is trying to conceal it. Hidden because the human eye was never built to see at this scale. Our eyes evolved to notice movement, light, color, danger, faces, weather, distance across a landscape. They did not evolve to see redshift. They did not evolve to combine millions of galaxies into a three-dimensional density map. They did not evolve to sense dark matter. The cosmic web had to be discovered by instruments, mathematics, patience, and comparison. It is one of the great examples of science showing us a universe larger than perception. And once the web is seen, the old image of the universe changes. Space is no longer just a dark background with galaxies floating in it. Space becomes a structured arena. The darkness has geography. The emptiness has shape. The galaxies have addresses. The voids have histories. The clusters have supply lines. The invisible matter has a skeleton. And the largest map we can make is still not guaranteed to be the whole map. This brings us back to the human scale, where the story began. On Earth, the Milky Way appears as a pale band across the sky. Most people will never see even that clearly, because city lights hide it. The idea that our galaxy itself is one point in a local group, and that the local group is embedded in a much larger cosmic structure, already stretches imagination. Then the web says, keep going. The galaxy is not the end of the map. The group is not the end. The cluster is not the end. The supercluster is not necessarily a single object. The visible web is not necessarily all of reality. Every layer opens into a larger layer until the limit is no longer matter, but observation itself. That is a rare kind of fear. It is not the fear of danger approaching Earth tonight. It is the fear of scale, of being inside something so enormous that even our largest maps are partial. It is the fear that the universe is not only bigger than we once thought, but organized on levels we can only barely detect. Yet there is also something strangely comforting inside that thought. We are not floating in a meaningless scatter. We are inside a structure. Our galaxy has a cosmic address. Our local group has a place in a larger flow. The light from distant galaxies carries clues from the web. The first light of the universe still helps explain why the web formed. Even from one small planet, we can begin to reconstruct the skeleton of everything visible. That is not small. That is one of the greatest achievements of astronomy. The universe did not make itself easy to understand. It is too large, too dark, too old, and too strange for that. But it did leave traces. It left patterns in galaxy positions. It left background light. It left gravitational distortions. It left clusters, voids, and filaments. It left enough evidence that creatures on a small rocky planet could realize they were not living inside a random sky. They were living inside a web of galaxies, a web of dark matter, a web of motion, history, and future separation. And the most unsettling part is that the web does not end where our imagination becomes tired. It continues to the edge of our observations. It may continue beyond them. It may contain regions whose galaxies will never be known, whose voids will never be mapped, whose clusters will never send light that reaches our telescopes in a useful form. So when we say the cosmic web is bigger than we can imagine, we are not using exaggeration. We are describing a real problem. Our minds evolved for fields, forests, rivers, and skies. The universe built filaments across hundreds of millions of light years. Our maps reach far, but horizons remain. Our telescopes improve, but light has limits. Our theories explain much, but dark matter and dark energy still hide their deepest nature. The web is therefore both a discovery and a reminder. It shows us that the universe has structure. It reminds us that structure can be larger than sight. It shows us that galaxies are connected. It reminds us that connection does not last forever. It shows us that darkness is not always empty. It reminds us that most of the architecture may never shine. And perhaps that is the final lesson. The largest thing we can map is not a wall, a sphere, or a single object. It is a pattern, stretched through time, held by gravity, shaped by dark matter, slowly changed by expansion, and partly hidden by the limits of light. It began as tiny differences in the young universe. It grew into the highways where galaxies formed. It opened vast voids between them. It gathered clusters at its intersections. It gave our galaxy a place in a structure far larger than the Milky Way itself, and it may be only the visible portion of a larger reality beyond the horizon. That is why the cosmic web is not just bigger than we imagine. It is bigger than the kind of imagination we were born with. To picture it, we have to borrow the eyes of telescopes, the memory of ancient light, the bending of space-time, the statistics of galaxies, and the mathematics of a universe still expanding. Only then does the pattern begin to appear, not as a simple picture, not as a finished map, but as the largest visible architecture in existence, a structure made from darkness and light together, a structure that connects galaxies while the universe slowly carries much of it away. A structure so vast that even the part we can see is already more than enough to remind us that the cosmos is not merely filled with things, it is shaped. And we are living inside that shape. But even that shape is partly hidden by our own galaxy. There is a region of the sky where mapping the distant universe becomes especially difficult, because the disk of the Milky Way lies in the way. Stars, gas, and dust inside our galaxy can block or confuse the view of what sits beyond. Behind that bright foreground, parts of the larger cosmic structure are harder to trace. This is a strange situation. The galaxy that gave us a home also hides part of the map around that home. So astronomers use different kinds of light, different surveys, and different techniques to see through or around the foreground. Infrared observations can help where dust blocks visible light. Radio observations can reveal gas. X-ray observations can show hot cluster material. Galaxy redshift surveys fill in wide regions. Gravitational lensing provides a separate way to infer mass. The cosmic web becomes clearer only when many incomplete views are combined. This is another reason the web resists simple storytelling. It is not discovered in one heroic picture. It is assembled. It is corrected. It is tested against bias. A bright galaxy may be easy to include in a catalogue, while a faint galaxy at the same distance may be missed. A survey may cover one part of the sky deeply and another more shallowly. Dust may hide one direction. Instrument limits may shape what appears visible. Every map has to be treated not as the universe itself, but as a measurement of the universe. That does not weaken the story. It makes it stronger. Because after all those limits, the same broad pattern still appears. Galaxies still cluster. Voids still open. Filaments still connect regions. Clusters still sit at intersections. The web survives better data, better instruments, and better mathematics. It becomes less like a guess and more like the shape that keeps returning when the universe is measured carefully. There is also a hidden rhythm in the web left by the early universe. Before atoms formed, ordinary matter and light were coupled in a hot plasma. Pressure waves moved through that early material. Later, when light decoupled and the universe became transparent, those waves left a subtle preferred scale in the distribution of matter. Today, astronomers can look for that imprint in galaxy surveys. It is not a visible ring in the sky. It is a statistical feature, a slight preference in how galaxies are separated on enormous scales. That feature is known as baryon acoustic oscillation. The name sounds technical, but the idea is powerful. The early universe rang in a way that left a faint ruler inside the later cosmic web. By measuring that ruler at different distances, scientists can study how the universe expanded over time. A pattern in galaxy positions becomes a tool for measuring cosmic history. This is what makes the web so valuable. It is not only large, it contains measuring marks. Those marks help test dark energy. They help compare the early universe with the universe now. They allow the web to become part of a cosmic distance ladder at scales far beyond individual stars. The largest structure becomes an instrument, if we know how to read it. And because the web is so large, even small errors in our understanding matter. A slight mismatch between prediction and observation could point toward survey bias. It could point toward incomplete modeling of galaxy formation. Or, if it survived every test, it could point toward deeper physics. That is why cosmologists care so much about precision. The web is not only beautiful, it is a laboratory spread across billions of light years. The laboratory is still expanding. New surveys are designed to map more galaxies, more shapes, more redshifts, and more weak lensing signals. They do not simply take prettier pictures. They measure the growth of structure. They compare matter distribution across time. They search for how dark energy may have affected the web. They look for whether our model of dark matter still works when tested across the largest available maps. This is where the calm beauty of the topic meets a serious scientific tension. Our standard model explains a great deal. It connects the early universe, dark matter, dark energy, galaxy clustering, and the cosmic microwave background into one framework. But the ingredients are strange. Dark matter has not been identified as a particle in a laboratory. Dark energy is still a name for an unknown cause of accelerated expansion. The web fits the model well enough to be one of its great successes, yet the model is built around things whose nature remains deeply uncertain. So the web gives us confidence and confusion at the same time. It confirms that we are not totally lost. It shows that the universe follows patterns we can model, but it also points directly at the missing pieces. If most of the scaffolding is dark matter, then we do not yet know what most of the scaffolding is. If the future of that scaffolding is shaped by dark energy, then we do not yet know what is driving the future. The map is sharp, but the materials remain mysterious. This is not waffle. It is the central problem. We can draw the skeleton of the universe before we know what the skeleton is made of. That sentence would have sounded impossible for much of human history. Earlier, astronomers struggled to understand the size of the Milky Way. Then, galaxies beyond our own were recognized. Then, galaxy clusters became known. Then, redshift surveys showed that galaxies were not scattered randomly, but arranged in huge patterns. Then, dark matter and dark energy became necessary parts of the explanation. The scale kept increasing, and each increase forced a new kind of humility. The cosmic web is the result of that long change in perspective. It is what appears when the universe is no longer treated as a sky full of points, but as a three-dimensional, evolving structure. That evolution is still happening today. In dense regions, galaxies continue to interact. In clusters, hot gas continues to record violent histories. In filaments, matter still traces the gravitational lanes between larger nodes. In voids, isolated galaxies evolve differently from their crowded cousins. The present-day web is not a finished sculpture. It is a slow process caught in the middle. If we could accelerate time, the transformation would become obvious. Clusters would draw in nearby material. Some galaxies would merge. Gas would be consumed or stripped. Star formation would fade in many places. Voids would become more dominant in volume. Bound islands would remain while unbound structures drifted out of contact. The web would not vanish at once, but its meaning would change. At early times, the web was a builder. It gathered matter and created the conditions where galaxies could grow. At middle times, it is a map. It shows us the large-scale arrangement of matter and lets us test cosmology. At late times, it becomes a memory. It leaves behind bound remnants and ancient records, while much of the wider pattern recedes beyond practical observation. That three-part story gives the web a beginning, a working life, and a kind of ending. Not an ending where every filament disappears from existence, but an ending where the connected cosmic landscape stops being equally visible or reachable from any one place. For a viewer on Earth, this can feel distant. Nobody wakes up worried that the cosmic web will change tomorrow. It will not. Human lifetimes are tiny compared with these processes. But the point of a space documentary is not only to ask what affects us next week, it is to expand the scale of what we understand as real. On that scale, the web is one of the most real things there is. It explains why galaxies have neighborhoods. It explains why the universe has deserts. It explains why some regions are crowded with clusters, while others are nearly empty. It explains why the map of matter looks like foam, roots, nerves, rivers, and lightning all at once, even though none of those images truly captures it. It explains why looking farther out is also looking farther back into stages of the same growing pattern. It also tells us something about our own location. The Milky Way is not isolated in a random field. It belongs to a local group. That group sits within a broader region of cosmic flow. Nearby galaxies move under mutual gravity. Andromeda approaches us. Farther structures shape velocities. Voids and dense regions both influence the large-scale motion of matter. Our galaxy is part of a cosmic environment, not a lone island. This changes how home feels. Home is not only Earth. Home is not only the solar system. Home is not only the Milky Way. In the largest possible sense, home is a position inside the cosmic web, a point in a vast pattern created by the earliest unevenness of the universe and reshaped by gravity ever since. That does not make daily life less important. It makes daily life stranger. Every ordinary room, every street, every ocean, and every quiet night exists inside a galaxy that sits inside a structure too large to see directly. The cosmic web is not above us like a ceiling. It surrounds the history of everything we know. The atoms in our bodies were made in stars, but the places where those stars formed were influenced by the larger distribution of matter. The galaxy that hosted those stars grew in a dark matter halo. That halo formed inside a larger environment. The environment was part of the web. The chain from the cosmic microwave background to a living planet is long, but it is not disconnected. This is where the web becomes personal without becoming sentimental. The cosmic web did not form for life. It did not aim at Earth. It did not choose the Milky Way. But without large-scale structure, the universe would not have built galaxies in the way it did. Without galaxies, there would be no long history of star formation and chemical enrichment. Without that history, rocky planets and living chemistry would be impossible, at least in the form we know. So the web is not just a distant arrangement of galaxies. It is part of the deep background of why complex things can exist. That is a different kind of vastness. Not the vastness of distance alone, but the vastness of dependence. A tiny planet can depend on processes that began across the whole early universe. A person can look at a sky that seems local and be unknowingly connected to an ancient pattern larger than any myth, empire, or map ever made. The final image, then, should not be a single galaxy. It should be a slow pullback. Earth becomes a blue point. The solar system becomes a small arrangement around one ordinary star. The Milky Way becomes a spiral in darkness. Nearby galaxies appear, groups become visible, clusters brighten like cities. Filaments stretch between them. Voids open like black seas. The map expands until individual galaxies become almost too small to matter, and the structure itself becomes the main thing. Then the image should pull back again, as far as observation allows. The web continues, not perfectly, not evenly, not as a solid object, but as the largest visible pattern made by the universe. And at the edge of that view, the question remains open. Does the pattern continue beyond what we can see? How far? With what variations? With what histories, clusters, voids, and galaxies that will never send us a usable signal? We do not know. That uncertainty is not a failure of imagination. It is the boundary between evidence and everything beyond evidence. The observable cosmic web is already enough to overwhelm us. It contains billions of galaxies arranged in structures so large that our everyday language begins to break. It reaches from the first measurable ripples of the young universe to the future isolation of bound galactic islands. It is mapped through light, gravity, redshift, and statistics. It is built from matter we can see and matter we cannot. And still, it may be only a section. That is why the subject deserves the word cosmic, not because it is merely located in space. Because it belongs to the entire story of space. It is the universe remembering its beginning, organizing its present, and revealing hints of its future through the arrangement of galaxies. The cosmic web is bigger than we can imagine, because it is not one thing to imagine. It is a structure, a history, a measurement, a mystery, and a warning. It tells us that the universe is not empty chaos. It tells us that darkness has form. It tells us that the brightest galaxies may only be markers on an invisible framework. It tells us that our maps are powerful but incomplete. And it tells us that even when we finally see the pattern, we may still be seeing only the part of the pattern that light has allowed us to know. That is where the journey ends for now. Not at a wall, not at a final edge, but inside the largest visible structure we have ever discovered, with every galaxy, every cluster, every filament, every void, and every unseen thread pointing toward a universe far larger than the human mind was ever meant to hold.